can't pause the recording, unfortunately. And so we're trying out the acid base. We inventory now. We found the strongest base out of the three, which is amide, and then we only have one acid present. So we only have one acid. If we're all bases, then it's easy because all the bases want to accept protons, but there are no acids, so nothing's going to happen. There would be no reaction. And the same thing, if we had a solution of all acids, is anything going to happen? No. And so you could have the craziest strong acid around and still get no reaction to occur because there are no bases around. Yeah. And so strong is just a relative term because it's relative to what you're mixing it with. Now, if you have a crazy strong acid and you put in a crazy strong base, then you're going to have a violent reaction. Not explosive, but well, it could. I mean, potential steam explosion, superheated water, but nothing like Texas City. But going back to this, okay, so we don't have any choice. It's going to be water or nothing, and so water is going to be the victim. You got three bases. All three bases want to attack water. Well, which one is going to be the highest probability for a successful attack? NH2 minus. So the most likely reaction to occur, and we don't know if it's going to occur or not, is amide and water, which forms hydroxide and ammonia. We just do a simple proton transfer. And then we label this. Water is our acid. We don't know if it's stronger. It's the strongest present, but now we're doing the comparison. Amide is our base. Now, what's the acid, what's the base going backwards? Because hydroxide is also, did you know hydroxide's amphoteric too?
Whoa.
Yeah.
Whoa.
Hydroxide's amphoteric. Hydroxide occurs on the acid side. Do you see hydroxide's an acid? And it occurs on the base side. It just so happens that hydroxide is a much better base than it is an acid. In fact, it's such a weak acid, we really don't consider it much of an acid. But still, it could. But then again, wait a minute. What we form here are two bases, hydroxide and ammonia. So this is base-base, isn't it? No, this is difficult because both these species are amphoteric. And so we don't know how it behaves until we react it. And so to figure out which one's the acid, which one's the base, we have to reverse this. Otherwise, if you get into the mindset that hydroxide is always a base, then you're going to be wrong sometimes. Because I might give you a special reaction where the hydroxide actually acts as the acid, and then you're wrong. And so to avoid that, we take each reaction case by case, and then we look. I mean, hydroxide could be either. So, is it the base?
Yeah.
And how did you determine that?
Because if you look at it backwards, you see that it received it.
Yes, exactly. That's how you determine it. Because if we go backwards, hydroxide gains the proton, so that's the base. That's the only way we determine it. We don't look at a chart like this and say, oh, hydroxide is a strong base, therefore it's going to act as a base. But we don't do that. We look at the reaction itself and see, because that means ammonia is an acid. And normally you don't think of ammonia as being an acid at all. Ammonia should be a base.
Well, then there's an acid.
But here it is. Here it is acting as an acid. All right, now once we determine these, then what we'll do is we'll see, which one's the stronger acid, water or ammonia. And so we go to the acid side of the chart. Here's water, here's ammonia. Water is a stronger acid. And so we're going from a stronger acid to a weaker acid. And that means because of the conjugate relationship, the bases must follow the same pattern. And that is amide must be a stronger base than hydroxide. And that's true. And this is a stronger base, and this is a weaker base. And so this is our driving force here. And so we're good. And so actually there is a reaction. There was no reaction for metathesis, but there was a reaction for acid base. And so typically this is what we'll do when we analyze this. If you had to analyze, can you imagine this? If you had to analyze reactions looking at combination, decomposition, precipitation, combustion, all those categories, was that an easy thing to do? No, and so this is much easier, and this is why I for one, like to categorize this in this way, because then we see only 3 types. The only thing we didn't look for is redox, and so we'd have to look for potential redox reactions just to make absolutely sure, we got all the potential reactions covered. We aren't looking at redox just yet. We're going to do another one. We're going to look at iron 3 chloride and silver nitrate solutions. Iron 3 chloride and silver nitrate. Usually we want to go in this order because it's easiest. We go metathesis, then acid base, and then redox.
Now, I have a question. When one of them is if both of them are soluble, then you don't have to write water on the reactant side. But if one is soluble and the other,
We don't, even if one is soluble, we don't necessarily have to write water. Let's go ahead and do this since we don't have that much time. Iron 3 chloride, what's the formula for that? FeCl3 plus AgNO3. Both of these are soluble and both are aqueous, so we're left with this. This is a simple double replacement metathesis reaction. What are the products of this?
silver chloride and nitrate.
Iron 3 nitrate, okay, and silver chloride. Okay, then we look for driving force. Is there a driving force? Yeah, what is the driving force? Precipitate of silver chloride. And then we'll balance this. We need 3 silver nitrates and we get 3 silver chloride. And so then we're done, right? We're done because we have a metathesis reaction that occurred. That is a precipitation here. And so this would be the CE, then we write the IE and then the NIE. The NIE would just be silver ions plus chloride ions yield silver chloride. So you could do that yourself. The NIE would be silver ions plus chloride yield precipitated silver chloride. Done? No. Not necessarily, because there could be potential acid base and redox. And so when we think about the inventory, we have, let's think about acid base. Iron 3, is that a good proton acceptor or proton donor? No, although iron 3 is a bit more complicated. We'll talk about this when we get into Lewis. Iron 3 actually occurs here as this. It's a very strange looking formula. But this actually is iron 3. It's an acid. And it's a decent acid. It's stronger than hydrofluoric acid, stronger than acetic acid. It's a pretty decent acid. So we'll talk about this later, but not right now. Iron 3, you don't really think. Chloride, is that a good acid or base?
No.
Silver ions, good acid or base?
No.
Nitrate. Nitrate is it's a base like chloride. We already talked about chloride. What about nitrate?
Very, very.
It's so weak that,
Not considered.
yeah, it's not really considered much anything. But yeah, maybe accepted it. But in other words, for acid-base reactions, let's talk. So we got reaction. We have a driving force here, which is the precipitation of silver chloride. And so we got metathesis, check. And then we look at acid-base. I'm speeding things along because there's not enough time. But acid-base, it turns out there's no reaction for acid-base. You can go through all the steps and you'd see that there's no reaction. And so that leaves one more, and that's redox. And so let me just write the steps in redox really quick, and then we'll do redox next time. And so step 1 for redox. Inventory. Step 2 for redox. find the strongest oxidizing agent, or OA for short. And so oxidizing agents are like fluorine. You know, fluorine is what we call electron poor, wants electrons. Step 3, find the strongest reducing agent, Ra. The strongest on our chart is lithium metal. 4, react the strongest OA with the strongest Ra. So react above, making sure, actually, I'll just say, by combining the half reactions. In this case, for redox, we always use half reactions. We just don't do it in one step. And so react the above by combining the half reactions, making sure electrons cancel. 5, simplify, usually get rid of spectators, and determine driving force. The driving force for redox is going from a stronger OA and stronger RA, so SOA, SRA, to weaker OA and weaker RA. It turns out there's a conjugate relationship for oxidizers and reducers, just like acids and bases here. So let's show that as well. Fluorine, electron poor, electron rich?
Poor.
Electron poor, wants electrons. And so fluorine takes electrons. Once it takes those electrons, is it going to let go of them? No, it holds on to them. And so fluorine is the oxidizing agent, and its conjugate reducing agent is fluoride. Its conjugate is extremely weak. Fluoride doesn't let go of electrons because otherwise fluorine wouldn't want it. All right. And then let's look at lithium. Lithium, electron poor, electron rich. Electron rich. It easily gives up electrons. That means, does lithium ion have a strong attraction for electrons? No. Otherwise, it wouldn't easily give up the electron. And so it's easy to separate. So lithium is a powerful reducing agent, but its conjugate oxidizing agent is extremely weak. So that's a conjugate relationship there, and I'll stop here. Thanks.